Let's talk about partial differentiation. If we have a function of one variable, then the definition of the derivative is familiar to us. We will write the difference of f in x0 plus h and f at x0, and we will divide this difference by h and then calculate the limit as h goes to 0. If the limit exists, then the value will be the derivative of f at x0. We can use this definition to find the derivative of the function x squared. Well, let's calculate the derivative at some point x0. Here we use the definition and we write the definition of the derivative. Well, what is our function? Our function is x squared, so we just take the x0 plus h to power 2 and we subtract x0 to power 2 and divide by h. To get further, we need to simplify this. We need to expand it in this way. And it seems that there's a mistake. Now everything is correct. X0 to power 2 will cancel out. And we can divide by h. Then we calculate the limit. And it seems to be 2 times x0. So the derivative at x0 is 2 times x0, so we have this differentiation formula. For differentiation there are many notations. One is this d over dx of x squared is 2 times x. Then one option is to put the comma there. x2 prime is 2x. You can pronounce this as prime. And we can also denote the differentiation by using a capital D letter. There are many differentiation formulas. For example, if we have some monomial, we can differentiate in this way. The derivative of the exponential function is very easy. Derivative of the natural logarithm is 1 over x. Derivative of sine is cosine, and the derivative of cosine is minus sine. For the other trigonometric functions or their inverse functions, we have also these differentiation formulas. They are not so easy, but if we need them, we can find them. Then there are also some general formulas by which we can calculate derivatives. One important one is the derivative of a product of two functions. Of course, we can use this one too. We can use this formula to give the formula for the quotient, derivative of the quotient. Then we have the differentiation rule of the composite function and the differentiation rule of the inverse function. Well, how does this formula look? It looks a little bit complicated. Especially we need to remember that inside here this function we have the derivative of f in the denominator, and the argument there is the inverse function of f. Here is an example about the formula of the derivative of the inverse function. We want to differentiate the function square root of x. Square root of x is the inverse function of the x squared function. For the x squared function, we know that the derivative is 2x. So we will have that the derivative of square root of x is something like 1 over 2 times t. But what value will t get? Well, t will be equal to square root of x. And here is our derivative. We know that if we have some function which has a sharp corner, then the derivative will not exist in that point. For example, if we take the function absolute value of x, it will have a sharp corner in the origin. So this means that the derivative does not exist in this point. The derivative would give the slope of the tangent in this point, but now in this point it's not totally clear how we could draw the tangent here. In sharp corners we have this problem and the derivative does not exist. We can get this result also by calculating. We have the formula of our function, and let's restrict to the case where x is not 0. So our formula is this one, and we can differentiate these expressions here to get 1 and minus 1. So it seems that the derivative of f would be now constant function. It would be constant minus 1 before the origin, and after the origin it would be constant 1. And in the origin the derivative of f will make a jump. We could even draw a picture of the derivative of f. It would be constant function until the point 0 and then make a jump, and again it would be a constant function. So it seems that in the 0 something problematic happens. If in 0 we calculate the one-sided limits, it means this is the limit when h goes to 0 from the positive side, so h is a positive number here. We would get that this one-sided limit is 1. On the other hand, this one-sided limit h goes to 0 from the negative side would give the one-sided limit minus 1. Because these one-sided limits are not equal, the limit does not exist. Limit does not exist, so the derivative of the function does not exist. Let's practice how to calculate the partial derivatives. So now we will have a function which has two variables x and y. And if we would like to make a graph of this kind of function, we would need to have a third variable here. And let's see. In this case, the graph of the function would be a surface. It would be some kind of cup surface there, like a cup. So here's our graph, like a cup. You can drink tea or coffee from the cup. If we would, from the function, we would set that x is equal to 0, then x squared would be 0, and we would just get a function y squared. Well, y squared equal z would be a parabola. Now the names of the axes would be y and z. So this is an example of a function of two variables. Let's have some more functions. If we take this kind of box, we can study the volume and surface area and the space diagonal of this box. These three things are functions of two variables. If we assume that our variable k would be changing, let's say increasing by some amount, we can then see how will these functions behave. Will they increase? The speed of change is a derivative. So we will get some derivatives also in this case. Let's define the partial derivatives. For a function of two variables, a partial derivative with respect to the first variable will be denoted in this way. Here is a funny looking letter. The name of the letter is dog. What is the partial derivative? Well, it's again a limit of a difference quotient. The difference here is that in variable x we have also put plus h there, and in this term plus h is not there, and then we divide by h. If the limit exists, then the limit will be the partial derivative. Well, let's calculate the partial derivative of the volume with respect to k. So to the place of k we will put k plus h, and here just k, and then we form this difference quotient and we try to calculate the limit. Well, here these k's will just cancel out and we will get that the limit is a squared. On the other hand, let's calculate the partial derivative of the volume with respect to a. So now to the place of a we will put a plus h, and here no h, and we form this difference quotient and we should calculate. Well, a plus h squared is this one here, so it seems that a squared will cancel out. So our limit will be equal to 2 times a times k. So when we differentiate with respect to k, k just disappears from here. When we differentiate with respect to a squared will become 2a. So partial differentiation, you want to differentiate with respect to some variable. Think that all other variables are constants and then calculate the derivative. Derivative of a squared with respect to a is 2a, and we can put our constant k there. So for the volume we obtain that the derivative with respect to k is equal to a squared. When k changes by the amount delta k, the volume will change by the amount delta V, and delta V is equal to the product of the partial derivative times the change of k. The partial derivative is a squared, so if we have the situation that for our cube we have a equal to 10 and k equal to 25, then a squared will be equal to 100. So by using the partial derivatives we can express the changes in the function when we know how much the variable changes. If we would like to differentiate this function here with respect to k, we see that the first term is a constant and disappears, and in the second term k will just vanish. So this 0 and this vanishes and we get 4a. So in this way, by using the partial derivative, we can get see that the rate of change for this surface area is this 40. If we want to take the formula of L and differentiate that respect to k, we can write the formula in a little bit different way. Now, when we differentiate with respect to k, the power 1/2 will fly there. The power will get a little bit decreased by 1, and we get the derivative of the inner function. The derivative of the inner function depends only from this term and will be equal to 2k. So this is our derivative and we can write it in this way. So we get that the rate of change of this L is this one here. If we would be initially in this situation, we would have the volume 2.5 liters, surface area 1200 square centimeters, and this would be the length of the space diagonal. If then the k would increase with 2 centimeters, then the volume would get increased by this amount, surface area by this amount, and the space diagonal would get longer by this amount. And the new values would be this, and this. So partial derivatives are a useful way to find the rates of changes of functions.